But this is not all. This is not the entire chain. This is a part of the chain, the last part of the chain, which is just providing the context and getting the answer from the Gemini. This does not have the retrieved, the retrieval part yet. So that one will come from the create retrieval chain. So the RAG. Hello everyone, welcome back to my channel. Today we are going to dive deep into RAG, which is Retrieval-Augmented Generation. I'll explain the entire concept in great detail, and I'll also implement an end-to-end project in RAG, which will have all the lines of code explained, and I'll do it in Google Colab so that any of you, regardless of whatever laptop you have, whatever you have, you can code along and you can understand each line of code in great detail. So it will be an end-to-end project, and this is going to be the agenda for today, and let's dive right in. Okay, so first we need to build a basic understanding of Retrieval-Augmented Generation, how it works and why is it useful. So LLMs, as you know, like GPT, you have used, I guess, GPT, Claude and everything, they contain a lot of knowledge within their pre-trained weights. For example, that can be surfaced by prompting the model and generating the output. But these models, they also have a tendency to hallucinate or generate false information. You must have seen it in your life as well, indicating that the parametric knowledge which is possessed by an LLM, it can be unreliable a bit. So they are trained on millions and trillions of tokens, and these LLMs, they try to fetch the information from those tokens, but sometimes there can be conflicting information, sometimes there can be information that is not correct, and therefore it hallucinates. But LLMs, they have the amazing ability, the super ability to perform in context learning. So what is the context? Which is the information that we are providing in the prompt. So this context learning is defined as the ability to leverage information which is within the prompt in order to produce a better output. So I feel that like the prompt plays a very important role, because if you can provide in the context, suppose you want to know about MCP, suppose you want to know about RAG. So if you provide in the context in there, in the entire prompt together, so then it's all done. So then you will be able to understand and you will be able to implement and use the information perfectly. And the LLM will also not hallucinate, and it will be able to use the contextual information perfectly, and it will be able to give the correct answer. So with RAG, we basically augment the knowledge base of an LLM by inserting the relevant context into the prompt itself. So it can be the system prompt, it can be the user prompt. Better to put it in system prompt and then keep asking questions, because then otherwise it will be like, it will be a lot of tokens, a lot of input tokens, it will slow down, it will cost a lot. So it's better to put everything into the system prompt. So you can say, for example, I want to know about MCP. And then you provide many documents which has MCP generation, and you want to talk about how to use MCP. These are all there in big documents and all. So basically, these things are the ones that matter the most. So if you put in, like, suppose you have, 15 or 16 pages of MCP, and you provide the context of the MCP into the LLMs, even if the LLMs, they don't know about MCP, because it's a relatively new concept. So we cannot expect LLMs to know about MCP, which have been trained on, let's say, 2023 data or something like that. So in that case, if you provide the context, then the LLMs know that, okay, so this is the context, and we know what to do with the context, because we know how to extract information from the context. So that is the entire thing of the RAG. So it is very simple. It's just that you are providing the context into the LLM prompting. And then, for example, let's say you are implementing a customer chatbot. Okay, so basically in customer chatbot, you want to, train the model. You don't want to train the model. One thing is definitely fine-tuning. You can fine-tune the model on the policy, and then it will give the answer. But suppose we don't want to fine-tune. Suppose the policy keeps changing. We can't fine-tune all the time, and fine-tuning requires so many GPUs, so many memory, and so much time, cost, everything. Suppose you don't want to fine-tune. You want to use the LLM as is. So you can have to provide the context of the policies. Suppose you want to have this kind of policy in your company. Suppose you are a lawyer and you have a lawyer chatbot, which is a lawyer assistant. So in that case also, you will need the entire thing in RAG, which is a Retrieval-Augmented Generation. So let's break it down. So Retrieval-Augmented Generation. So LLMs, these LLM like Claude, GPT, they do generation, and Retrieval-Augmented means you're providing the context. So it's not only retrieving it from the training data, which everyone does, that's okay. It also retrieves from the context that you're providing, which is the most important. So let's say given an input query, we normally respond to this query with an LLM by simply ingesting the query. Say, what is MCP? And generating a response with the LLM. But this Retrieval-Augmented Generation, or RAG, it modifies this approach by combining the LLM with the searchable knowledge base. So in other words, we first use the input query to search for relevant information within an external dataset. Then we add the info that we find. So this is the retrieval. We are retrieving from the context. So MCP, we are saying And our input data set completely, it's divided into, embeddings and all. So they are all like, the context is basically, the entire document, 15 pages. We can't provide 15 pages into the prompt, because then that will be so many input tokens. So we don't want to do that. So basically what we are doing is that, so this entire context, that is the 15 pages, 20 pages, 200 pages of policies, of laws, whatever it is. So that one we are dividing into embeddings, and these embeddings we are storing in some database, vector database. And then when we give the prompt, say what is MCP, so from those embeddings we are going to search similarity search the context, which is the basically the input, which is this MCP, and we're going to find out everywhere where those MCP is present, and we're going to fetch those embeddings and those chunks of data into the context. So we're not sending the 200 pages. That's impossible. We can't send 200,000 pages of data into the LLM. That will just consume all your, cost and everything in just one go. That we don't want to do. And not relevant either, because suppose you have the document of MCP, you have it about RAG, you have it about LLM, you have it about, I don't know, you have it about nature, earth, whatever, but you don't want that. You want just MCP. That's and surrounding text context of that. So that is the retrieval part. So we are adding the info that we find from the, database to the model's prompt while generating the input. So which basically allows the LLM to use this context, which is by its in context learning abilities, which every LLM has, even the open source ones, closed source ones, everything, to generate a better and more factual response. So look at this. So here, basically, they are first pre-trained and then they undergo alignment via SFT and RLHF, which is the reinforcement learning. You don't need to worry about it. Just say that they're pre-trained on millions and trillions of tokens, and they have a huge knowledge base on which they're trained on. And after this, we have the search engine, which fetches the relevant data. So then this data we add into the prompt. So the LLM has idea of its entire training data and the context which we want it to focus on mainly. So therefore, it's able to give very good responses. So basically, by combining the LLM with a non-parametric data source, which is this retrieval that we are fetching, we can feed the model correct, specific, and up-to-date information, and this will reduce hallucination by huge percentage. Okay, so let's discuss about the steps of RAG first. So first, it requires access to a dataset of correct and useful information to augment this LLM's knowledge base. So basically, we must construct a pipeline, you can understand. So the first thing is basically, let's say we have a lot of PDFs, we have a lot of markdown, we have a lot of TXT files. So first thing is going to do, we are going to chunk the data. That is, we are going to split it into sets of shorter sequences, which typically contain around 100 to 500 tokens. So check this out. So we have this markdown format, and then we have the LLMs that are first pre-trained, and then we clean the data, pre-processing, that's okay. And then the raw text is there, and then we do the chunking, so that we are now dividing them into small parts. Now that this is done, so now we are going to do is, like, there are many algorithms to do this chunking properly that we'll discuss later. But let's first understand the entire flow, entire pipeline first, because that's what is most important for interviews, for GATE exam, for colleges and everything. Okay, so first thing is that, and next thing is going to be searching over the chunks. So as you can understand, if we have made these chunks, obviously now we are going to search it. Suppose we have the query as what is MCP. And now what we're going to do is, like, give the user query, and then we are going to search over these chunks, finding out which is the highest similarity with our with the query that we are giving. So basically, these, like, once we have cleaned our data and separated into searchable chunks, we basically build a search engine for matching the input queries to chunks. So today what we are going to do is we are going to use default ones, which are from the LangChain library. But you can write your own function for that. You can experiment with it. These are all like good problems to solve. And then next thing is going to do is, like, build a dense retrieval system. Once we have searched it, once we have chunked it, then we have searched it, then we are retrieving it. And now we are going to retrieve that. So after that is done, next thing is the generation of the output. So once we have retrieved the relevant textual chunks, the final step of RAG is to basically insert these chunks into a language model's prompt and to generate an output. So as you can see right here, so this is generating the model output perfectly. So basically, RAG comprises the full end-to-end E2E process of ingesting an input query, finding the relevant textual chunks, concatenating this context with the input query, and using an LLM to generate an output based on the combined input. So these like approaches, they have variety of, variety of different paths and all. But we are going to do a very simple one today to understand that you can have an end-to-end RAG implementation of a project. So the main benefit of this is to reduce hallucination. We don't want any hallucinations, and LLMs do. I mean, even the best of the best LLMs hallucinate. So this is the RAG is basically to stop hallucination completely. That is like hallucination means generation of false information. So basically, we don't want that at all. Since we are providing the entire context, what we want, everything we are giving to the LLM, we just want the LLM to give the final correct answer. So therefore, it can never, there's no opportunity of the LLM to hallucinate at all here. And it's able to access up-to-date information because, these training, the LLMs, they generally trained on 2023 data, 2020 data. So these are all very outdated. Like AI changes every single day. Every single day, there's new information, new concept, new things coming up, and people search those things. There's political information, there's natural information, there's so many things that are coming up. So we need up-to-date information, and we obviously can't train the data of this on these LLMs every now and then, every time. So that's not possible. That is why RAG plays the most important role here. It not only provides it provides just the updated information. You can do web search and provide the information chunks from there. These are all RAG. They're all based on retrieval-augmented generation. And there's obviously data security because you're not training the data, but you're using it to generate the information. That is why it's very, very important. And, it's very easy to implement as well. So these are all the benefits of RAG, and we are going to start implementing the project now. Okay, so let's get started. Okay, so as you can see right here, we have the Google Colab. So just open a new notebook and then we are going to use it. So you won't need GPU for this, so it's okay. So you can just normally connect. And let's name it to be RAG project. Yeah, let's name it to be RAG project. And let's start implementing. First, we're definitely going to install. We are going to need LangChain mainly for this. So LangChain is a Python library, very famous, and you will need an API key. I will show you how to get an API key as well. Yeah, so let's get started. So first thing is basically you are inside this. So let's do not equal to pip install upgrade in case we already have some of the packages installed. And this is just another argument. LangChain community. We're going to use all these, RAG functions, basically how to divide them into chunks, how to retrieve the chunks. These are all we are going to use the LangChain libraries. That is why LangChain is most important here. You can implement your own, but we are not going to do that today because that will require a long video, very, very long. So there are many ways. I'll cover I'll cover all of them in subsequent videos. And we have Beautiful Soup. So Beautiful Soup 4 is basically a library that generally used to scrape the web. So basically here we are going to use it not to scrape the web, but to scrape the documents and to search engine. Basically kind of like a search engine over all the the chunks that we have made and we have stored of the document when we are doing an input query, as I mentioned. Okay, so let's install all this. And we're also going to require the model that we're going to use today is Gemini, because Gemini doesn't have much rate limit and it's very easy to use and it's free as well. So we are going to use that. Okay. I'm sorry, this is LangChain Chroma. And next thing is going to be pip install q LangChain Google Gemini, basically. Google Gemini. Whatever, I mean, it's just that from where we are going to get the model. The model is basically the Gemini 1.5 Pro, which we are going to use today. It's pretty good model and it's also cheap. So that's what we're going to use today. Okay. I am not sure why this is coming, but let's see what happens. So also we'll just do a restart the session. Okay. So now next thing we are going to do is import OS. And we are going to provide the environment variables, all of them. os.environ. Environ. First thing is going to be LangChain tracing v2. LangChain tracing v2. Let's keep it as true because we do want to see the stack traces and all the errors and all. So, okay, LangChain endpoint is going to be api.smith.langchain.com, which is perfect auto completion. And os.environment is going to be LangChain API key. And here we are going to provide your API key. So I'm going to show you how to get the API key. Let's see, LangChain API key. So LangChain API key we are going to get. So let's say here, and we want to create an account here. So, let's use Google account and then go inside this. Go and get started. There you go. So now I have provided the LangChain project as well, which is RAG, and the API key as well, and the endpoint. Just provide the API key here. I'm not going to share my API key, but you can get it easily. It's free completely for everyone. Okay. Now the next thing is very important. We will need this, which is the Google API key, because we are going to use the Gemini 1.5 Pro model that I said. So let's get the Google API key. I'll show you how to get the Google API key as well. So, just do a normal search, Google API key. And even if you're stuck anywhere, just use ChatGPT. I'm telling you again and again, just use ChatGPT, use Claude. They'll tell you every single detail. So yeah, just go inside Google AI Studio. Okay, so now that we have run this as well and this as well, so we have the API keys and everything with us ready. Just put in your API key here. That's it. Okay, so now that definitely there's this warnings, we get a ton of warnings. So, just stop these warnings. Warnings, dot filter warnings, ignore. That's it. Okay, so now comes the initialization of the embeddings. So what is embedding? So basically you have a huge document, as I said, and you want to divide that into small embeddings. And these embeddings you're going to store in a vector database. And then we are going to search the database. And then we are going to get the retrieved results, which is a retrieval augmented, and then provide that into the context of the LLM or the GPT, or here, for example, is Gemini. And then we are going to get the answer. That's it. So first thing, we need the embedding model. We need a model for generating the embeddings. So let's see. From LangChain, Google Gen AI, import Google generative AI embeddings. That's it. We're going to generate the embeddings, and Gemini embeddings. We're going to use Gemini for embeddings as well. Gemini embeddings would be equal to Google generative AI embeddings. Let's see. Embeddings, and then it's going to be model name. Okay. So now then we are going to just provide in the, we have the Gemini embeddings and the Google generative AI embeddings, and we are going to provide the model name. So the model name is not the correct title. So model is going to be models slash, it's going to be embedding 001. That's it. So this is very important. Gemini embeddings and model equal to models and then embedding 001. That's it. And now next thing is going to be from LangChain. Again, Google Gen AI. Import chat Google generative AI. So this is the model that we are going to use. This is the Gemini 1.5 Pro that I mentioned. So yeah, that is this. So the model we are going to use is, the first one was the embeddings model. So this is the model that we're using for generating the embeddings of the document. And this is the model that we are using for generating the answer of the LLM text. The main LLM that we're using. You can use OpenAI as well. You can use your own hosted model. You can use your open source model, whatever it is. It will all give the more or less the same answer. Model would be equal to Google generative AI. And then here we are going to give the model as Gemini 1.5 Pro. And this is a very important, a convert system message to human as true. Why this is important? Okay, so this convert system message to human is very important. Why? Because Gemini models, they generally didn't used to have this user and system messages particularly. So system message, user message, and assistant message. These are the three things which are most important. As we know, we have used OpenAI API. So this argument is very important, so that because LangChain it uses system prompt and then user prompt and then assistant response, but Gemini did not use to support this. That's why this is important. You can also skip this right now because we are using 1.5 Pro. I think it should be fine. But if you are using 2 or something, then it's also fine. You can remove this prompt as well. But we are just going to keep it because it's fine. You can keep it or you can remove it. So it's better to just keep it. So, and let's see now. Print model dot invoke hi dot content. See, this is the model. So we know that we have initialized the model perfectly, but the model is answering the questions. So, and the Google API key that you provided works, and it's free for everyone. And the system message is fine, but this is just hi, the response to hi. So which will come under user message. System message we'll have to provide separately, and since we have provided this argument correctly, so therefore it should be fine. Okay, so now the next thing that comes is creating the retrieval chain. So the first thing is basically Gemini embedding. So we haven't created the embedding, so we have initialized a model, and now if we just provide this embeddings model into the pipeline, it will generate any kind of embedding from the documents that we are providing. So next thing that comes is retrieval. So we are going to create a retrieval chain for our RAG implementation. So, okay. So as I said, so this retrieval is kind of like a search engine, and we know that Beautiful Soup is best for web search, web scraping. So that is why we are going to use BS4 here, or the Beautiful Soup 4. So from LangChain, import hub, and then from LangChain dot chains, import create retrieval chain. So this is the retrieval chain that we are going to use, the standard function that we're going to use from the LangChain library, because we're not going to write it down on our own. Great. So this is the retrieval chain that we have imported from LangChain.chains, and will also require, to basically after retrieving all the documents, we'll need to get them together and then pass them in as context to the LLM, right? So for that, we'll also need a library. So for that, this is the library that we are going to use from LangChain.chains.combine documents. Will require import create stuff documents chain, and then after that we'll require the Chroma. So basically we are using the Chroma database as a vector database to store all the embeddings and the chunks of the document that we are creating. So that's why we are going to import Chroma. So from LangChain.Chroma, from LangChain Chroma, we are going to import Chroma. That is the database that we are going to use to store all the embeddings. Obviously, because we'll just, do this embedding creation at the start for the whole document, and we're not doing actually, dynamic documents. So it's like the whole document we are doing at one go, and we're storing it in the Chroma database. And now next, for whatever queries we are doing, we are going to get from that database based on whatever, the chunks or the context that we are searching for. For example, say MCP. So we have a lot of context based on MCP in the Chroma database. So we are just going to get all those, the embeddings from the Chroma database and then pass them in as context to the LLM, and the LLM is going to use that for the answer. That's it. So let's move on. So from LangChain community, we are going to get the web-based loader, because we are going to load basically the documents that I'm going to provide in for, storing in the vector database and asking the LLM to generate the question answers based on that. So basically that data, that web page is the web page. So we are going to use the web-based loader for that. So because we are downloading from the website. So the LangChain also provides, document loaders for that. So LangChain community. LangChain is pretty awesome, to be very honest. For these kind of tasks, LangChain is pretty awesome. For RAG-based tasks, for generating things that are like mostly for context and for AI agents. I'll make many projects on AI agents as well. But for these RAG kind of tasks, LangChain is the best. I would suggest all of you, to go through all the documentation. I'll also go through the documentation with you. But overall, just go through the documentation. It's really awesome. So from LangChain community to document loaders, we are going to import the web-based loader. Yeah. So now that we have this, yeah, that's okay. And then from that, after that, we are going to do from LangChain. So this is basically what we are going to import here is basically the chat prompt template. So what is that? So basically, the LangChain is different and Gemini has different. So the LangChain has different format, different prompt structure and all, and Gemini has different prompt structure and all. So therefore, in order to, we are going to make a pipeline, right? So that pipeline is also, we are doing it with the help of LangChain, so that we don't need to think too much and we don't need to set up everything. So it's going to be done through LangChain. So that is why we'll need the chat prompt template, because, we are going to pass it in a certain format that LangChain accepts, and then LangChain is going to convert that in a certain format that Gemini accepts, and then the answer will get back in a certain format in the way we want it. So that is why the entire thing, it can be done with the help of chat prompt template. So let's do that. So LangChain core dot prompts is going to import chat prompt template. Exactly. So this is very important. Try to remember this one. This is for, generating the prompt structure properly. Okay. So next thing is basically so this is the next thing that we are using. So LangChain text splitters. I'll tell you what the use of this is. Import recursive character text splitter. So what is this for? So this is for basically creating the embeddings. Basically, for example, when you are given a data set, suppose, not data set, for example, when you're given a web page or a document or a PDF or a markdown or an HTML, whatever you are given. So then you need to basically divide the text into, split the text into proper chunks, proper set of groups of characters, right? So this text splitter is going to be help us to do that. You can use your own custom functions as well, as I say again and again. So, but this is just a standard way of doing it. Okay, so now next thing is the loader. So let's write the loader. So that is what I'll show you which website we are trying to, load here and put it into the, make the embeddings and put it into the database, Chroma database. So let's see. Web-based loader. And then web path. Web paths is going to be. You can put in multiple paths as well, but there's a particular website that I'm going to use. So this is the particular website that I'm using. So as you can see right here, it's a very large website. It's about AI agents, and it has references, challenges, and, a github.io page basically. LLM powered autonomous agents. So let's see, this is an agent system overview, and then tool use, and then there's planning, self-reflection. Yeah, there's many things that are going in here, and there's component 2, which is memory, long short-term memory, component 3, yeah, whatever. I mean, there are many things here. So this is the post that we are going to use. Something I found online. But you can use anything you want, but it's just what I'm going to use. And next thing is going to be, so we are using the, BS4, which is Beautiful Soup 4. So that is why we are going to, need this to be like sort of, you can put in dict here as well, but this is also a dict, but it's just the way I prefer it to be used. So parse only is going to be equal to bs4.soupstrainer. It's a class basically. Class is going to be post content and then post title, all of them. We're going to use the content, we're going to use the title and header, everything. Because otherwise, well, I mean, if you don't use all the things, then it becomes difficult for the, LLM to understand what exactly is going on. You can't just provide the content, raw content. You'll also need the title. You'll also need the header. That's why these are all important. Great. So now we have the Beautiful Soup args. So, okay, let's go. So next thing comes is Doc would be equal to loader.load. We're going to load the data. Okay, I think there's something missing. Yeah, so this is working. So this is the web-based loader, and this loader we just now, got it. And then we are doing the loader.load. So now let's see what the doc looks like. So the error was basically in this, HTML code. So basically I copy pasted it again and it was working now. So in case you're wondering what went wrong. So let's see the doc. Okay, so let's see the doc right now. It's a huge doc because it is like scraped from the website. Let's see the website. So building agents with LLM. Definitely we must have, yeah. This is the thing. And then building agents with LLM, the entire thing basically. It has gotten the entire doc. Great. In the form of a document loader because we have used the LangChain library. LangChain document loader. So now that we have got the doc, next thing that comes is text splitter. We are going to split the doc into smaller texts with some overlap because we want to capture the context as well when we are, searching and storing in the database. That is why. So we can't do exactly like exhaustive, exclusive. We have to do, overlap of certain number of context so that we know which chunk comes after which chunk and what exactly is the flow of the document. So these all things are small things, but these are all very, very important and will impact the quality and accuracy of your answer a lot. Okay, so let's see. This is a recursive character splitter, character text splitter. Chunk size is 1000 and chunk overlap 200. This is a standard one that we are using. So 1000 chunk size means that we are going to divide that into 1000 chunks, and there will be 200 chunk overlap between each of the subsequent chunks. So this is the text splitter, and now we are going to generate the splits of the text. So we'll see how it looks like. Yeah, split documents doc. So let's see how the splits look like. Let's see. Okay. So first is definitely the page content is this and date and then estimated reading time and then building LLMs, everything together. Yeah. So now let's see. This is the splits that has come up. So, there is like, yeah, see, this is memory and then this starts with memory. So these kind of overlaps are there. So this overlap is definitely there. And even if sometimes it's not visible to the, open eye, it is still there because LangChain does it internally. So, these chunks, they all have overlap of 200 characters in between them. And the chunk size is total 1000 of each. That's it. So now let's see. Now let's create the database, initialize the database, and then store these embeddings into the database so that when we're searching for it next, we'll be able to find that easily. So let's do that. So chroma would be from documents. Documents would be the splits and embedding is the Gemini embeddings because we're going to use the Gemini embeddings that we created, the embedding class that we created, the model, whatever, embeddings model that we are going to use to generate these, like each of these text chunks into embeddings and then store them into the vector database. So there it is. And the next thing comes is the retriever would be equal to vector store dot as retriever. So this is basically the retriever class that we are making. So we are going to retrieve from the vector database. So that is why we have created this class of retriever. So let's see the retriever class. So this is the vector store retriever and definitely the chroma tag. And then, yeah, this is the chroma object and vector store is basically the chroma, the vector database that we are keeping all the, chunks in and that will use for our basically retrieval. So this is the retriever as well. This will be used to retrieve basically. It's not yet retrieved anything because we haven't asked it to retrieve anything. Okay, now comes the system prompt where we'll be passing in the context basically, the system prompt and the context. So we are going to put that in a placeholder and we are going to put that in when we are actually making a call. So what do I mean by that? Let me show you. So system prompt is going to be, you are an assistant for question answering tasks. Next thing is use the following pieces of information to generate the context basically. Following pieces of retrieved. All these parts are very, very, very important. Try to understand everything. It's not too difficult, but it's very important to answer the question. And then if you don't know the answer, say that you don't know. Exactly. Do not hallucinate. This is the most important reason why we're using RAG, because we don't want the LLM to hallucinate. If you wanted to hallucinate, then we would have just, not even gone to this much difficulty. We would have just allowed it to, write whatever you want. But that we don't want. We want it to be very much reliable. And if it doesn't know, then it doesn't know. That's it. Use 3 sentences maximum and keep the answer concise. So why exactly are we giving this if you really are wanting to know? So that is why, because, suppose we say the question, what is MCP? And we have gotten the context to be MCP. And we're now saying that, or maybe suppose we are asking, suppose what is AI agent? And we have the document based on MCP, right? So then it is not there, right? So it will just go inside inside this training history and try to find something. But, it is wrong, because in the context it's not there. So it will just say, I cannot help you, give me more context. That's why we are providing this, because you don't know the answer, then don't say you don't know, don't try to guess. That's it. And use 3 sentences maximum and keep the answer concise. This is fine. Yeah, and then there's slash and then that is like the context. So this is system prompt. And now the chat prompt. This is the most important thing. And we made the chat prompt template. So now we are going to use it. Chat prompt template dot from messages. And then we are going to pass in, system as system prompt. And we're not going to put the message holders right now, because we don't have the chat history. We are doing a basic RAG at first, and then after this we'll do the conversation history aware RAG retriever. So the chat prompt template is system prompt, and then human is going to put in the question or the input, whatever it is. Now next thing that comes is the question answering chain. So it is going to be create stuff documents chain. So this is chain that we are creating, the pipeline that we are creating. So this is going to give in the model and the chat prompt. Right, this is the question answering chain, because we are going to provide the question answer, right? So it's just for the question answer. So it's going to provide in the chat template, which has the input and this, and the system prompt, which has the context, right? And then the next thing is the model, which is a Gemini 1.5 Pro. But this is not all. This is not the entire chain. This is a part of the chain, the last part of the chain, which is just providing the context and getting the answer from the Gemini. This does not have the the retrieval part yet. So that one will come from the create retrieval chain. So the RAG chain is basically this. It's a question answering chain, which is just using the LLM and the retrieved context, already retrieved context. We don't have the context yet. So this is the last part of the chain, the last part of the pipeline, this one, question answering chain. So which gets the model and the retrieved context and the input, and then gives the answer based on that. And RAG chain is basically, it retrieves the context from the Chrome database. So that is why it will require the retriever class. Remember this one, it will require. And it will require the Gemini embeddings model, which the model that we are using. I think we have already provided the model here, so we won't need anything else. We'll just need the retriever and the question answering chain. So this would be the entire chain together, where this is the last part of the chain. I hope I make myself completely clear. So this is the create retrieval chain. This is the retriever, and this is the question answering chain. So now we have the entire thing together. So this is the entire retrieval chain. This is the entire RAG chain. Our project is complete. The basic RAG project is complete. So this is the entire RAG chain. So now let's see what the response comes out to be. So RAG chain dot invoke. The same way you invoke, and you put in the input. I hope you put in the input as what is. Let's see what we want to search here. Self-reflection. We can ask self-reflection as well. We can ask reflection. Let's try to see something more difficult. Maybe MIPS or MRKL. Okay, see, this is MRKL and they did an experiment. Yeah, so these are the 2 paragraphs on MRKL. So let's do that. That seems to be a bit, something that maybe the Gemini 1.5 Pro, which is a bit older model, might not have in its in its like training data. So let's do the MRKL one. Let's do that. MRKL. Okay, so this will take some time. Yeah, it does not take time. Well, so this is the input. Great. What is MRKL? Now the context. You know, this context thing that we are passing in. So this context is the document. Let's see. Figure MRKL. See, this is the MRKL. First thing about MRKL. Next thing, the document is fetched based on MRKL again. They did a context on this LLMs and all tool format and everything. You know, just one thing, if you see here, let me show you one important thing. So this paragraph does not have the MRKL word, but considering the fact that this paragraph is secondary, like the second paragraph to the first time MRKL is mentioned here, that is why it knows. It knows that this is based on MRKL. That is why it has been able to provide this as the context. So this is the power of the overlapping things that I mentioned. So since that they have this one, there's significant amount of overlap with the next chunk. So this is the next chunk maybe, and this is significant amount of overlap, and then this also has overlap. So it knows that these two things are related to MRKL. And this one, not this one, there's some images as well that are related to MRKL. But you know, these two paragraphs are definitely there. So these are all the context that is coming in, and the answer is here. So the answer is basically from the Gemini. It has gotten the context. See, again, I'm going through it. Gotten the context. This entire context is gotten here. That's the system prompt. Now chat prompt is system prompt, and the human is the input. So input is what is MRKL. And now it has the context. It knows the question. It gives the answer. It's a neurosymbolic architecture. Models can be this. Acts as a router. Whatever it has gotten here, it is going to answer. Neurosymbolic architecture, see, same thing. Neurosymbolic architecture for autonomous agents. It does not use anything else. It is not hallucinated. It is knowing perfectly what answer to give. This is awesome. And this is RAG. There you go. This is the entire RAG system, basic RAG system that we have implemented. This explains everything that I explained in great detail. And you know, we'll do a conversation history aware RAG agent in the next upcoming videos. But for now, this explains the RAG system completely. I hope you have gotten the entire video. And if you did not understand anything, I would encourage you all to go through it again. And you know, if you have any questions, to mention in the comment section. I hope I have made myself clear. I have explained each and every line of code in detail. And you know, if you have any questions, you know, definitely drop them in the comments and I will get back to them. And you know, drop a like if you like the video and subscribe. And thank you.